Hi, my name is Aditya Ramdas. I'm a fifth year graduate student and the year is 2014. Welcome to the set of tutorials on an introduction to probability and statistics, at least just the basics that you might need. And maybe it's almost a review of stuff that you should already know from undergrad, and maybe some few extensions to higher dimensions that you might not have seen before. Now, the first topic we're going to look at is, it's a discussion of what's called events and sample spaces. Now, even though you may not explicitly need this in your ML course, it's bound to come up at some future point in more advanced courses. An event is often denoted by little omega, is one outcome of a random experiment. The sample space, capital omega, is the collection of all such outcomes of some random experiment. Okay, so here are some examples. When the random experiment is tossing a coin, then the sample space, that is omega, is heads and tails. Those are the two possible options. And an event is any one of these options. So if you actually toss a coin and it turns out heads, then omega is basically H. A different experiment would be, for example, rolling a die. In this case, the sample space, which is a set of all possible outcomes of the experiment, is just the die shows 1, 2, 3, 4, or 5, or 6. Right? So just note that in this case, the outcomes were letters, not even real numbers. In this case, they're real numbers. But basically, in a discrete setting, when the outcomes are discrete, it need not be a real number. It could just be an identifier like H or T to mean heads or tails. Another example where the experiment could be, say, waiting for a bus. Over here the space is continuous, so the space is 0 to infinity. Now just think of that as being measured in seconds or hours or something like that, as the time that you would end up waiting for the bus. It's some positive real quantity, and at least if you're in Pittsburgh, there's no real upper bound on that quantity. Next example would be, say, where the experiment is to pick a random human being and measure his height. And let's say we're measuring the height in feet, then the space would be somewhere between 1 foot and 9 feet. Okay, that's just an example. So it's any continuous value in 1 to 9. Right? So that's what we mean by an event and a sample space. Now things get a little bit tricky, but it's useful to return to this at some point if you get confused. The concept of a random variable is quite important. Now, a random variable basically assigns a real number to every possible outcome. Okay, so for example, if the outcome is tails, maybe I'll assign x the number 0, and if the outcome is heads, maybe I'll assign x the number 1. So for the coin tossing experiment, this is one example of a random variable. It need not be this. I could have also assigned x as -1 if I got a tail. I could have also assigned x as +2 if I got a head. That would be a different random variable, right? So a random variable is just some assignment of a real number to every possible outcome. Here's another example. Suppose I measured the height of the random human being, got a number between 1 and 9. My random variable could be height squared. So whatever number I got, say I got 6.3 feet, then its x is 6.3 squared. So it could have just been height, it could be square root of height and so on. But this is one example of a random variable. To formally explain it, a random variable is a function. It's a function from your sample space to the reals. So every element of the sample space is given a real number, right? So x of omega is a real number. Okay, so in this case, x of omega equal to t is 0 and x of omega equal to h is 1. Right? So this is the way we formalize it. Intuitively, you can just say it assigns a real number to every outcome. formally it's a function from omega to r. Now, a probability measure, okay, so I'm not getting into the details of measure theory, but it's sufficient for you to understand maybe the high level basics for the moment. But a probability measure is a function from subsets of outcomes to 0, 1 that satisfies certain properties. These properties are that the probability of the whole set, the probability of the entire sample space omega is 1. The probability of the null set represented by phi is 0. And the probability of A union B, that is the probability that A or B happens, is the probability of A plus the probability of B for disjoint events A and B. As an example, for unbiased coins, the probability of heads would be 0.5. So this is a set. The probability of this set occurring is 0.5. The probability of this set occurring is 0.5. And accordingly, the probability of H and T, the probability of this set is 1. This is omega, so you can think of it that way. P of omega is 1. And another way to actually think about it is when A is a subset of omega and then P of A actually means the probability that the outcome of the random event, so the outcome of the random experiment omega is in A. So when I say P of H here, this set H, I mean what is the probability that the random outcome of the experiment is in H? That's 0.5 for an unbiased coin. Now again over here the probability of H comma T is to be interpreted as the probability that the outcome of the random experiment of tossing a coin, the probability that that random outcome is in the set H or T. Well, that probability is 1 because there is no other possibility. It has to be either heads or tails. Right, so just remember that we often write P of A when we actually mean P of the outcome belonging to the set A, right? And similarly, sometimes we don't write P of a set. Sometimes we write something like this. Suppose X is a random variable. We'll write what is the probability that X is equal to 5. So remember that X is a function from omega to R. When we say probability of X equal to 5, we really mean what is the probability of all those outcomes such that X of omega is equal to 5. Right? So there are many outcomes for which X of omega could be 5. And I'm going to take the probability of that entire set. And remember that the probability of a set means the probability that the outcome of your random experiment lies in that set. Now similarly, the probability that X of omega is equal to 5 is actually the probability that omega lies in X inverse of 5. So just like probability that omega lies in A, here the set A is actually X inverse of 5. So remember that if X is a function from omega to R, then X inverse will go from R to some subset of omega. Right? So X inverse of 5 will give you all those elements of omega that map to 5. So when I say P of X equal to 5, what I really mean is what is the probability of all those random outcomes of your random experiment actually belonging to the set X inverse of 5. As an example, I can ask what is the probability of X less than equal to 1 for my coin experiment. What is the probability that X less than equal to 1? Well, this is actually the probability of all those outcomes such that X of omega is less than equal to 1 because X of omega is a real number, right? Now this is just the probability that omega lies in X inverse of omega lies in X inverse of minus infinity comma 1. That's this set. X of omega less than equal to 1 means that omega lies in x inverse of minus infinity comma 1. And that just is the same thing as saying omega lies in h comma t. Those are exactly the events for which x maps to the set minus infinity comma 1. Specifically, it maps to only 0 comma 1, but there's no harm in writing it this way. And what is the probability that omega lies in h comma t? That's 1, because there is no other possible outcome. So of course, this is a trivial example in which you could have immediately seen for a coin, in which I assign 0 and 1 to heads and tails, the probability that x is less than or equal to 1 must be 1, right? But here's the more rigorous way of arguing about it. We really assign probabilities only to subsets of events, right? Only to like omega, phi, and a and b, where these are events or subsets of the sample space, right? So these are subsets of the sample space. More formally, they are elements of a sigma field and so on, but I don't want to get into those specifics. And we only assign probabilities to such subsets. And so when we say that the probability of a random variable taking on a value, we really mean the probability that the outcome is contained in the inverse of x inverse of whatever set we want. So you should return to this at some point if you're getting confused about these concepts. Let me summarize again everything I've said on this page. A random variable is a function from omega to r. It assigns a real number to every possible outcome. A measure, a probability measure, is a function from subsets of outcomes to 0, 1, such that it assigns the probability 1 to the whole set, a probability 0 to the null set, and the probability is additive for disjoint subsets of omega. And this is just a question of notation, what we mean when we say P of A, and what do we mean when we say P of x equal to phi or P of x less than or equal to 1. To summarize, in this lecture we discussed events, sample space, probability measures, and random variables and so on. This might seem a little bit abstract, but in the next lectures we'll discuss mean and variance of random variables and start talking about things like joint distributions of pairs or vectors of random variables.